All right, the topic that we're going over this time is going to be divide and conquer algorithms. And in particular, most of what I'll focus on are binary search and ternary search, but we'll also talk about some more general divide and conquer stuff at the very beginning and end. So remember that we are going through a series of topics now that are just general ways to solve problems. So we already talked about brute force and greedy and dynamic programming, and the kind of last area that we're going to look at is divide and conquer. So there's plenty of examples of divide and conquer. It's probably one of the most well-known, most used techniques in all of computer science. It's the basis for a lot of algorithms. So you have the standard binary search that we're going to be talking more about uh, in just a minute. You have things like quick sort uh, and merge sort. Those are all examples where you have something divided into two parts. You can handle those more simply on their own, and then you somehow bring them together. Uh, in almost anything that we have that are tree-based data structures are an example of divide and conquer approaches. And there's tons of other algorithms that are based on divide and conquer. So pretty much all the idea is that you take some big problem, you divide it into two smaller problems, and those are easier to solve on their own, obviously, because they're smaller, but they're not just easier to solve on their own. The fact that you break them up makes it tractable. Say, if it's n squared, now each one is n over 2. So instead of being the whole thing n squared, you've got two things that would be n squared over 4. So it's only n squared over 2 somehow to combine them. So it makes the overall process potentially a lot faster. And in particular, when we deal with binary search, it's not just it's not really divide and conquer, it's decrease and conquer is sometimes the term that's used. So the idea of binary searching is it is a decrease and conquer because what you're left with is is just a single smaller version. Uh, of the problem. Okay, so you go from trying to find something in a large range to now a smaller range, and you throw away the other part of the range. So it's not like you have to deal with both of them, like in general divide and conquer. Now, everyone, I think, is very familiar with the idea of binary search of values in an array, values in a sorted array. And of course, we've talked about this before. This is probably the most common thing that you see that's an example of this. But there are ways to extend the idea. And so what we're going to talk about today is mainly binary searching an answer, but the concept is still pretty much the same. So extending the idea of values in a sorted array, just to do a quick and very, silly reminder, if I've got a whole bunch of values here, 1, 3, 8, 12, 13, 15, 20, 23. Okay, so there's a bunch of values, and I want to say, is the value 9 in the array? I would first go somewhere in the middle, so 1, 2, 3, 4. Great, I made an even number, but go somewhere in the middle like there, 12, and I would say, is the number 9 greater than or less than 12? It's less, so I would look at the numbers less. Then I'd go to the midpoint there and say, oh, I look at 3. It's greater than 3, so I'm going to look at the remainder of the array that's bigger. I look at 8. It's bigger, and now I've found in between these two. I know it's less than 12 and bigger than 8, and it doesn't exist. So I say the number 9 does not exist in the array. So you can use this to find an element in the array. So this is the common thing. I hope everyone is very familiar with that idea and knows about binary search. Again, we've talked about that before. Okay, so a more general way of thinking about this is that we can have some function of values, and so we want to find where the function has some particular value. Okay, so let's think about this in algebraic terms because that's what you will be familiar with already. So if we have some function in space and that function is going in some way, and we want to find where that function takes on a particular value a, if it's a monotonic function that's increasing steadily, we can use binary search to find where that is. And the way this works is you start out with a low point. So let's say that this is going to be my low value, and you start out with some high value at some other point here. And we'll just go ahead and draw that there, where you know that the low is below the thing you want, and you know the high is above the thing you want. And then you pick a point in the middle and you test it. So we pick some value here in the middle. Let's pick something right there. And we say, is the thing that we want still too high or too low? So when we evaluate the function, we look at it and we say, oh, it's still just barely above that line. And so we would update and we would move the high value over to here. Okay, so this becomes our new high. So we check something in the middle, we move everything over to the midpoint, like wherever that middle value was. Either we bring the high value down or we bring the low value up. So if we do this again, we check another value right here and we say, okay, that point on the function is below, so we will move the low up to there. And if we keep doing this, we'll find that we move low the next time we check. Low will go up to there, and the next time we check, maybe the high comes right there, and the next time we check, the low goes right there, and the low goes right there, and pretty soon you've converged onto the thing that you care about. So this is something that you should be very familiar with already from math classes, calculus, other things, where you're trying to actually do root finding for a function. And you probably learned Newton's method, where you look at the derivative of the function and so on. We're not going to do that. It's just a very simple process of going of honing in on the function. So the general way that we would describe this is that we are looking uh, for a zero of a function. Okay, and so first of all, if we want to find f of x is equal to a, so if we actually don't want zero, we want to find where it's a, then that is the complete equivalent to find f of x minus a equals 0. Okay, so either way, this is finding a zero of a function. We're going to find where some function is 0. Either we actually look for the value 0, or if we want to find when it hits some value a, we can look at the function f of x minus a and look for the 0 of that function. So there's lots of very variable ways you can describe this and actually implement it, but that's always going to be the process. So we're looking for some 0 of a function. Now, the thing that makes this different from what you've looked at in math classes before is that the function uh, can be a complex procedure. So it's not necessarily some nicely defined algebraic or analytical function that you just plug a value into and you get a result out. It can be some complex procedure that you need to actually find an answer for. So I'm going to give you a couple of examples here in a minute of how this works and what it would look like so that you can picture how this concept gets used more generally. But that's what makes this different from just searching on an array. We've got some complex procedure, and what we need to be able to do is we need to be able to evaluate that for some input value. Okay, so there's some input value, there's going to be some x. So this x that we have there, we have to be able to provide an input value, and then we get some output from that. The other thing is that the function should have values below 0 and above 0 and be continuous. And almost always, although not actually always, almost always, you want something that is monotonic. Okay, monotonic means not increasing or not decreasing. Okay, so monotonic, so function like that is monotonic going up. Here's a monotonic function going down. A function like this is not monotonic. It goes up and then it goes down. Okay, so monotonic increasing, monotonic decreasing, not monotonic over here. Okay, and whatever the value of 0 is going to be, there needs to be some value where you can say, this value is clearly below 0, this one is clearly above 0, or above 0, below 0. And if it's a continuous function, as you know, if you're going to somehow go from above 0 to below 0, there has to be a way to do it. Now, I mentioned that it's almost always monotonic. I'll just mention this. It's rare that you would want to do this, but you can find some solution. You can't find a particular solution, but you can find some solution, even if it's not monotonic, as long as you have a point above 0 and below 0. So let's imagine that you had some function that went like this. Okay, and I have a point above 0 and I have a point below 0. Well, if I imagine doing a binary search on this, so I look in the middle and that's something below 0, that moved my low value up. And then I do midpoint there, it's still below 0, it moved that up. And notice eventually I'm going to, in this case, hone in on that particular 0, even though there were 4 others that maybe I might have hit. Okay, so again, not the sort of thing that we normally want to worry about, not a typical case, but it does exist. Sometimes you just need a solution when there could be multiple possible solutions. And then you can still use binary search as long as you find a point that's below, as long as you know some point below and some point above to start out with, and it's a continuous function. Okay, so then what does it mean to do binary search? I'll say let's start. And I'm just going to write them because it's easier for me to write low. That is, I'm going to say negative. Okay, but I'm going to assume a case kind of like this one here, where you're going from negative to positive. If you're going from positive to negative, then you just reverse all the positive and negatives here. And you start with a high that is positive. And then you are going to repeat the process where you define mid is going to be low plus high over 2. You find the midpoint of the low and the high. You evaluate f at mid. So you check the value at the midpoint. And if it is less than 0, then low gets mid. Okay, so you assign mid to low. Okay, so I'll just put equal, but that's assignment. Otherwise, so else you have high equals mid. Okay, so that's where I have some function. I know a low point, I know a high point, evaluate the midpoint. I say it's negative. Because it's negative, I move the low and this becomes the new low. So I went from this being low and this being high, and low moves there. I do it again, I do that, and you will stop when typically you stop when high minus low is less than some value epsilon. Okay, so when high and low are close enough together, you go ahead and stop. Now, this is one place you have to be very, very careful. Whether you want to actually stop when high minus low is less than epsilon, or sometimes you want to stop when f at high minus f at low is less than epsilon. Okay, and so what do I mean by that? So if I have something here, which is a function that is very steep, okay, let's just assume it's like a line going way up. I can have a low value and I can have a high value here, and I might say that that distance between the two, this distance right here, might be less than epsilon. But if you look at the value of the function itself, it has a much bigger range. Okay, so that value from there down to there, that is a much bigger value. Okay, and so if you say that you want an answer that's accurate within something, notice that if you have some point and you don't know where the point is in between low and high, it could be anywhere in there. The function could be anywhere between this low value and this high value. That's the zero could be anywhere between them. And if you just need the zero within some accuracy, that's one thing. If you need the function to have be close enough to zero, that's a different question. And in that case, you want to make sure that the red is there. So this one is the one that's marked in red. This one is the one that's marked in green. Okay, so do you actually want to say how far apart are these two? Or do you want to be saying how far apart are those two things? And again, it can work the other way as well. If you have a very shallow uh, function, you can have something where you have a low value here and you have a high value over here, and you'll notice that the difference in the function from here to here is very small, whereas the difference in the low and high values could be very big. Okay, so you always want to make sure that you're careful about which of these two stopping criteria you actually need. Sometimes people will mess up if they pick the wrong one. The other way you can often kind of hack it is you make epsilon a lot smaller than you really need. It just usually means you do a few more rounds of binary search and get your answer. Okay, so that's the particular way that this works. Let me mention a couple of examples here, just so you can see what these examples look like. So there's an example. It's on Caddis. It's not one that I can use. There's a 3D example where you have a block of cheese, and I'll give you a 2D version of it in just a second. But imagine that you have some block of cheese here, and it's Swiss cheese, so it's got all these little sphere holes inside of it. Okay, and none of the spheres overlap each other. Um, and you're wanting to cut this cheese into equal size pieces. So say it's 10 pieces. Okay, so I want to cut this into 10 pieces, and I want to know, where do I cut along this edge so that I get something that's exactly 1/10th of the volume? Because you can imagine, if the holes are in one area, you don't get very much cheese. If the holes are in a different area, uh, like far away from you, you get, very dense cheese. So you want to make sure that you give someone the same volume. Okay, so let's look at this as a 2D problem for a minute. Um, it's the same basic problem as 3D. Okay, but imagine that you have holes and each hole is a circle. We're going to assume that none of them overlap each other of different radii. Okay, something like that. So in this case, there's 4 holes that are there, and you want to know kind of what's the overall, how would I divide this so that I get, let's just say, let's make it easy. Let's say that we want to divide it into thirds, 3 pieces, each one equal volume. Well, how would we do this? So the first thing we would do is we would have some function that's going to say f of x, and I'm going to let x be some point along here, starting at 0 all the way up to d. So f of x is going to be the volume, or in 2D, it's area. I said this was a 2D problem. So this is going to be the area uh, from 0 to x. Okay, so, or maybe I'll do an a just so you can see it here, from 0 to a. So if this is a, f of a is the area of this cheese from 0 to a. Okay, now notice that this is not just a nice simple function. Okay, so how do I get the area from 0 to a? I would have to create some function here, something that is like the function, f and I pass in some double A, and I'm going to return a double for it. Okay, so I pass in some double A and I'm going to return sub double. And so what would I do here? I would take the volume from 0 to A. So let's call this distance here H. Okay, so I would say the base volume equals A times H. So in other words, that's how much the volume would be if there were no holes. And then you would have to loop through the holes. And you would say for each one of those, is it inside completely? And if so, subtract pi r squared. So you take away the whole volume. If it is inside partially, then you would calculate the portion inside and subtract. So if I had some circle and I was slicing because I just want to know how much of the circle is in that region there, we'll notice if I know the center here, I can calculate that, and I can calculate this area here just is based on radians. It's pi radians times the radius, and then I could calculate the area of this triangle right here because I know what this distance is. So I know the radius, so I know two of the three sides of the triangle. So I can calculate the other side of the triangle. I can calculate what that volume is. Okay. So I can get all of these different angles that I need to know, calculate the volume, or in this case, the area of the circle. In 3D, you can do the same thing with the sphere. You can imagine having some sphere, and if I slice that sphere off by some plane, I get some circle there where it got sliced off, and I can calculate the area of that spherical cap that's sitting out there on the end. But obviously, this is a more complex thing. Okay, so notice this whole thing, and I'm skipping a lot of the details of it, but this whole thing is not just a simple little algebraic function. This is something where I'm going to have a loop that I go through stuff. I'm going to have to do these kind of weird geometry calculations somewhere in the middle. And overall, out of all of that, I'm going to eventually return some volume, after I've subtracted off the holes for where things are. And so if you look at something here, if I want to know what the 1/3 amount is for this whole thing, I would first of all say, well, I could calculate the total volume. So the total volume is going to be, sorry, f is the function we used, is f at d at the farthest point. Okay, so we want to find some value a such that f of a equals 1/3 f at d. That's going to be the 1/3 mark. And we also want to find the second place and find b that's 2/3 f at d. Okay, and so we might say, oh, we cut it there for a and we cut it here for b. And if we make our cuts right there, we get three equal sized slices. I don't know if that's true. I'm just drawing something there. Okay, but you can imagine that those, notice the area from A to B, it's the narrowest, but it's also very dense. There's hardly any holes in it, whereas A has a lot of holes. It's the biggest part from B to D. There's one big hole in the middle there. So maybe those are about the same area, where those are. But how would I find this? If I wanted to find where f of A was 1/3 f of D, I would go ahead, I would calculate f of D, and then I would say, I know that f at 0 is less than 1/3 f of d. Okay, in other words, the function that I want is f at 0 minus 1/3 f of d. So let's just call this thing the target. So let's call this target t. So if I want to say f at 0 is less than t, it's the same thing as f of t is less than 0. So I start out, I have a point here at the very beginning that I know is less than my value. Okay, that's going to be my low. So this will be, so 0 can start out at my low. And I know that d is going to be my high value to begin with. And so the first thing I would do is I would check somewhere here in the middle. That would be my midpoint. And I would calculate the volume there. And I would say, is that volume greater than or less than t? If it's less than t, then it means this is like not far enough, so I would move my low value up. If it's greater than, I would move my high down. And so in this particular case, I know I would move the high value down to there because I haven't reached A yet. Then I would check the next midpoint. Okay, so I check the midpoint there, and that's going to be too small of a volume. Okay, so that volume is less than t, so I'm going to move the low value up and so on. Okay, I hope I said all of that correct. I hope this all makes sense. Main point here, main point of all of this, why am I going through all of it, is our function. Thing I want you to see is that the function is not just a simple little algebraic function. So even though I was drawing these pictures with graphs and stuff like that, and in fact, this is a continuous function, right? It's an integration of this area as you go. So it's a continuous function, but it's not something that's just easily evaluated that you can just plug in. Okay, one more quick example of this is I'll give you a graph problem. Okay, so there's a graph problem, something that we're going to talk about later, which is flow through a graph, max flow. And so the idea here is that you have edges between different nodes of the graph, and there's going to be sources, and there's going to be sinks, and so on. And so let's say that this is the source, and this is the sink. And there's going to be, and don't worry about any of the details of how this thing works right now, there's going to be edges between all of these things that give some sort of capacity or weight. Okay, so we've got all of these different edges, and they might all have different weights to them. So like, this one might be 10, 30, 20, 5, 18, 12, 10, 20, and 20, and 14, and 13. And I think that's about all of them. Oh, then there's one more here. Let's call that one 18. Okay, actually, let me give some unique numbers. I'll change some of these so I don't repeat them too much. 21 and so on. Okay, so the question might be, what's the minimum size that I need among these so that I can get the appropriate amount of flow from the source to the sink? Okay, that could be the answer. Maybe even you put something like the cost of all of these in there. Okay, so you have something like, what's the minimum cost? So maybe every one of these, that's the amount of flow it has, and then there's some amount of cost that it gives. So like this might cost $100, and this one might cost $80, and this one might cost $70, and this one might cost 30, and this might cost 50, and so on. Okay, so there's some cost. So you say, I want to minimize the cost. I'm kind of making this one up as I go. But actually, I want to minimize the cost so that I can get at least, some amount of flow, K flow from the source to the sink. And again, don't worry about how flow is calculated. That's not important right now. Just know that each of these edges has some value. It has some cost to it. It has some different costs associated with each edge of the graph. And so what you want to do is figure out what's the minimal cost that I need. I need to minimize the cost so that I can at least get the K flow. Well, you can already say, if you give me a cost, if you say f at x is the flow through the graph um, if only edges cost less than or equal to x are allowed. Okay, so for instance, in the graph up here, if I set x to 90, well, this top one up here would not work, but that one there would work, and you would be able to keep it and so on. Okay, so you have some function that's the flow through the graph. And so you want to find the points where the flow is not enough. Okay, so your low, you'll initially start out with a low value where the flow is insufficient. And high is where the flow is sufficient. Okay, so what values could you pick for low and high to begin with? Well, at first, you could set the low to 0, because obviously, if you had cost 0, you wouldn't have any edges, and there's going to be no flow through the graph. That's clearly insufficient. And flow being sufficient, you could set it to the max edge cost, whatever that is. So whatever the most expensive edge is, you say, what if all the edges are there? And you would run that to check, because if that doesn't work, well, then nothing would work. There's no way to get it, but presumably that's plenty to work. So you have high, the high value up here. This is one that is good. It's going to work, and the low value is one where it's not enough to work. And so you would then check mid. So you'd compute the mid, and you'd say, is the midpoint how much flow? You would calculate the flow. Okay. And is it too little? If it's still too little, then you update low. And otherwise, you would update the high. Sorry, my writing has gotten bad. Okay, because I'm realizing I'm spending a lot of time on this. Okay, so you get the idea here. So here we've got something where, again, we've got a low value and a high value. And the main point of these is my function in this case is not I mean, it's not even like a nice little graph function. It's just saying, how much would it take to get through? If I were to draw a graph, it would actually be something that would be like plateaued like this at some point. So you want to find what's the value right where you get the sufficient, something below that is not there, and then you get that value, and it's enough to get you enough load that brings you above it. Okay. Once you hit that edge length. So that's another example of a binary search. In this case, you're binary searching over a set of values. In this case, it's the values within the graph. So you could have made a big array of all of the edge weights and sorted it, and then binary search on those edges. And that's the same thing as what you're doing over here with the low, medium, low, mid, and high, is a binary search on the edges that are possible to use. Okay, so that's the idea of binary search. I want to introduce a different topic, though. It's a variation. It's probably one that you're less familiar with, but it's actually a very, very similar idea. And I won't spend a ton of time on it, but it is a cool thing. It is a ternary search. Okay, so ternary search, this works for graphs. Or I say graphs, so I'll say functions. With a single max or min. So it should be monotonic increasing, then decreasing. Okay, so a function that goes like that is what I'm talking about. Now, the whole thing works just as well if it were the other way around. You just reverse the signs of everything. So it's the exact same principle if you're looking for a situation like that, but we're going to assume it's a situation like this one. And so the goal is the goal is to find the maximum. Now, you remember from calculus, you can do this by like finding where the derivative is 0, and that's going to be where the maximum is. And sometimes you can do that even in problems that are meant to be a ternary search problem, or that are more naturally a ternary search. But that's not always possible to do. Again, if you think of having something where the function is not a nice thing where you can take a derivative easily, ternary search is your answer. So with ternary search, again, we're going to start out with two values. We will start out with low equals a value below the max, and high is going to be a value above the max. Okay, so you have some value here. This is going to be low, and this is going to be high. Okay, and so what we will do, we're trying to find the maximum point here. We're going to generate, instead of just one point, we're going to generate 2 points along the way. So we will generate point 1, or let's call it A. So I'm going to say A is going to be low plus high minus low over 3. So it'll go a third of the way. And B is going to be low plus 2/3 of the difference. Okay, so we would basically say A is the 1/3 mark, B is this mark. Okay, and here I'm going to draw just a slightly different function just so I can illustrate. So imagine that this is my function. So I've got my low value here, and I've got my high value here. Okay, and we generate A and B. Okay, so what we will then do is we will evaluate f at A and f at B. So if if f at A is less than f at B. So what does that mean? It means we plug A into our function, we calculate the value there. We plug B into our function, we calculate the value there. So this one is f at A, and this is f at B. Okay, we can actually determine something about what the shape of this is, and we can narrow our range. Again, we don't have to just compute exactly what the max is. All we have to do is be able to narrow the range down from what it originally started out as. Okay, so in this case, if A is less than B, like you see here, A is less than B, what that means, if you think about it, we've got 4 regions here, or sorry, 3 regions here. Why am I saying 4? We've got 3 regions here. We have the region from low to A, from A to B, and from B to high. And we want to say, is there one of those 3 regions that we know does not contain the maximum? And in this case, if A is below B, okay, and we know that it was monotonically increasing to a maximum and so on, if we know that's the case, then we know that there cannot possibly be anything in the region between between low and A. Okay, that's not possible to have to have the maximum in there, because you're going from something that's very low to something that's low, and there's some point higher. Now, it is possible that it's in this range, and it's possible that it's in that range. We don't know. Okay, we don't have any idea where the maximum actually is. So notice I drew this function, but imagine an alternative function. I'll draw it in green. Imagine an alternative function with these same values that went something like this. Okay, so that function, notice, has a maximum that comes after b. But in any case, there's no way to draw a function with a single peak where that peak would be between low and a. So in that case, what we can do is we can update low to get a, and otherwise we will update high to be b. Okay, So notice what we do, and we're going to just repeat this. So then we repeat. We're going to repeat this whole thing here. Calculate a new A and B for the new low and high, and we are going to repeat until basically high minus low is less than epsilon. Okay, so when you get the high and the low value close enough together, you say, I found my maximum point. That's where it is. Okay, that's where my max is going to be. Okay, so very simple operation. It only works when you have a function like this, monotonically increasing, then monotonically decreasing. Again, if it were shaped the other way and you're looking for the minimum, you just reverse the signs of the negative, so on. Okay, so f of a greater than f of b in that case. Okay. Um, so that's all we have. That's the ternary search idea. Notice instead of dividing everything by 2 each time, it's dividing it to 2/3, but asymptotically dividing by 2/3 is still logarithmic. Okay, so it's still log operations, even though instead of being log base 2, it's log base what is it? 3/2. So um, same basic idea. All right. I want to mention just a little bit more so that you can get some ideas of other things that fall in the divide and conquer more generally. And I will not spend long or give you examples on these, but there are techniques called spatial subdivision techniques. If you if you are if you are ever doing computer graphics, you will definitely run into spatial subdivision approaches. So these are like binary space partitions, quad trees, and octrees. The idea there is that you start out with some large region and you can divide it in. This is a quad tree here. You can divide it into 4 parts and you can say, can I say something about each of those 4 parts on its own? And if not, you can subdivide those parts further and you can possibly subdivide those further and so on. And eventually you can get down to a 2D region that you care about. Okay, that meets the criteria that you want. So there's all sorts of things. There's sort of extensions from 1D into 2D that are based on cases like this. Another thing for divide and conquer that I think is useful to realize what it is a binary exponentiation. So the idea is that you can compute powers, and you do this by basically dividing. It's a divide and conquer approach. Okay, so let's say that you want to compute x to the n. So if we want to compute something that's x to the n, one thing we could do is we could take x times all the way that times x, and you do that a total of n times. And obviously that's going to take a really long time. Okay, but it would be a whole lot faster if we instead converted this, and let's just assume n is even for now, into something that's x n over 2 times x n over 2. Okay, and now we only have to compute this, and we reuse it for the other one. So now we've computed x times x times x, and so on, and we only had to do it n over 2 times. And then we square that number. Okay, if things were odd, so this is going to be this is the even case. The odd case is going to be x times x to the n over 2 times x to the n over 2. Okay, so there's going to be one extra x there, but again, the rest of it is just x of n over 2. And of course, then you run into the same thing. How do I compute x of n over 2? Well, I can do that by saying x to the n over 4, and so on. And so if you think about what's happening here, basically the x's that are coming here, the reason it's sometimes called binary exponentiation is if you look at like a binary, version of some number Here you would say, oh, it's odd, so I'm going to include the x, and then everything else, I'm going to do that one time. That's my x over 2. And then, oh, now it's even, so I do x over 2 of that. Now that's even, x over 2 of that. Oh, now I've got another 1, so I've got one more, x to multiply there, and I'm left with this one. Oh, my pen's deciding not to work. So I'm left with those three. It's even again. Oh, now it's odd right there. And go down and oh, it's odd again. So I would have, in this case, 4 odd terms and so on. But you can basically see it's basically going down the binary version of the power that you want to compute. Okay, so it's much, much faster. You can compute powers of something very quickly. And you might say, do I really need that if I'm computing powers? There's all sorts of other ways to do powers of things. Yes, it's useful, and it's especially useful if you're doing things. Notice that I didn't say that these had to be numbers, and that doesn't have to be multiplication. Okay, so you can imagine that, say you're multiplying matrices together. Okay, so you're going to multiply the same matrix over and over and take a power of a matrix. Okay, so X doesn't have to just be a number, it could be a matrix power. You could do things where the operation between them is not just multiplication. It's like, some other operation, as long as everything would apply like that, as long as it's an associative operation. Yeah, associative operation, then the whole thing will work. Okay, so that's another example of computing powers, this binary exponentiation. So don't be surprised if you see some problem, maybe on a lab in the future, that involves using this concept to compute powers of a number more quickly, or powers of something, when it would be just painful to compute, or maybe even impossible to compute all n. You can do it in basically log n steps through this divide and conquer approach. I probably won't give you any quad tree things. I mentioned that because it's really nice. I like it in graphics. It's all sorts of spatial subdivision is useful. So it's useful for you to know about. Maybe there'd be something very related, but it's not likely to actually be something we cover in class in terms of a problem that you encounter, but it's a nice idea to understand. Okay, so that is everything about binary and ternary search, uh, and more generally divide and conquer approaches. I hope that was useful. Hope it made you think about what binary search is in a broader sense than what you're probably used to before this. All right.